One case we're showing our benzoic acid act as an acid, and the other case we're showing it act as a base. How would we know which preference we should run with?
One is accepting a proton, the one's giving.
One's accepting a proton, one's giving a proton. To accept a proton, what do you need? Electrons. A lone pair is the easiest thing to look for. It has a lone pair, so could it act as a base? Theoretically possible. Will it act as a base? Almost never. Okay? So the question becomes is how can we come up with a way to predict these? Because it's relatively easy to find hydrogens, it's relatively easy to find electrons. Deciding whether or not they're going to act as acids or bases becomes a little bit trickier. Okay? The way that you guys need to get used to figuring them out is drawing out the reaction and saying, was that a good idea? Okay? If it doesn't look like a good idea, then that was probably the bad thing or the wrong thing to do. Double back and try something else. Okay? But we can go through and actually quantify. To quantify, we'd look up at our pKa's. Okay? And if we look at the pKa's of benzoic acid, it comes in at roughly 4.2. And we look at the pKa of water, it comes in at 15.7. When we compare those two structures, or those pKa values, which one would we expect to act as the acid? The one that's more acidic, the lower pKa value. That means that bottom equation doesn't make sense to actually occur, okay? Because it's more acidic than water. So it shouldn't be acting as a base when it reacts with water. Does that make sense? You're just comparing those pKa's, coming up with some relative concentrations. The next part is then deciding, should this reaction go to form products in any reasonable amount? Okay, and there's a couple approaches to this. The first approach that we could go through and attempt is look at our acid-base rankings that we've already done. Okay, do we become more stable? Well, our rule is we always minimize charge. Does it look like we're minimizing charge? No. So that already suggests that's not a very good idea. Okay, but it might be nice if we could quantify this and back this up with some evidence. To do that quantification, we could go through and determine our Ka's and all that fun stuff, and our pKa's. Our pKa for benzoic acid was 4.2. We would look at the conjugate acid. So on the other side of the equation, we have hydronium ion being our conjugate acid. And that has a pKa of negative 1.7. Which is the stronger acid? The hydronium is our stronger acid. Well, what does our reaction want to do? We always want to favor the side of the weaker species in general. It doesn't have to be acid. It could be a base. It could just be nucleophile, electrophile. So if this is our stronger acid, we would expect our equilibrium to largely lie towards our reactants. So we could then add in some equilibrium arrows and show that specification or show that extra information. Okay? As you move into second semester, equilibrium becomes a much larger issue, and we really have to watch out for it. There are several reactions that are so heavily based off of equilibrium, the only way we get them to work is by using Le Chatelier's principle. Okay? First semester, we tend to kind of dodge that bullet for the most part. You see some Ka, pKa expressions pop up, but they're relatively minor. Okay? So we could see all those K expressions, and we can have a mild heart attack and just kind of accept that. The big thing you need to remember, the bigger your pKa, the weaker the acid. The smaller the pKa, the stronger our acid. That in conjunction with our systems always stabilizing, okay, should help us predict acid-base reactions or help us to decide, was that a good move to do? Okay, kind of makes sense? We did get here, didn't we? Okay, so I was off a little bit. We should memorize certain pKa values. Okay, and the one that I flagged, I believe, was the amine. We have to be careful when we look up the amine pKa, because the pKa that you typically find for amines is for the amine in its protonated state. We're looking at the pKa actually for that one of being 9. Very rarely do you see the pKa for the actual amine acting as an acid. Go down to its conjugate base. That's a pKa in at the 35 range. Okay. So watch out for that. Other than that, the rest of them are straightforward. You don't see anything else that's kind of bizarre or kind of wacky. For those of you moving into, say, biochem, the two that you should really address would be your carboxylic acid and the amine pKa, and in particular the amine pKa on the left-hand side of that. Why would we not look at the amine pKa of 35 in, say, biochem? In biochem, we're looking at living cells. What's our pH? About 7-ish. We can oscillate kind of up and down from that a little bit, but not very much. To get it to act, okay, as an acid, get that pKa of 35, we're looking at something that is exceedingly basic. So basic that it's probably dissolving most of the cell. Okay? Not generally a good idea for biochemical pathways. Okay? So just kind of be aware of that. So when you move into biochem, you'll see references to protonated versus deprotonated states. They're looking at a structure. So when we reference the amine, our protonated state for the amine is the one where the nitrogen is positively charged, 4 bonds. Okay? The deprotonated state, where it has a single lone pair. The protonated state for a carboxylic acid is directly shown. The deprotonated state, just take away that hydrogen. And you'd be looking at the balance between those two conditions at varying pHs. Okay? Why does this become important? All of our cells are made up of proteins, which are made up of amino acids. Some of those amino acids have acidic and basic functional groups on them. Okay? If we change the pH, those acidic and basic functional groups can go from being neutral to being charged. All we do is move a single atom. How could that possibly matter? I don't know. Did we just finish an experiment where when we changed the pH, the solubility of our compound went from being water insoluble to water soluble? Yeah, it makes a significant difference in the physical properties of our compounds. So if we fluctuated our pH, say, in our body, I don't know, a couple pH points, that could change our proteins from being water soluble to water insoluble, and having chunky solids move through your heart and bloodstream, not generally a good idea. Okay. So pH becomes really, really important if you have to move into biochem. Anything medicinal should be talking about it. Okay. Whether they address it at this level, who knows? Okay. The rest of them, kind of the big ones, alkanes and alkenes, pKa's up in the 40 range, which means what? Careful, that does not mean they're basic. pKa refers to acidity, and acidity only. Has nothing to do with basicity. Okay. They are exceptionally weak acids. It is very difficult to make them act as an acid. For those of you making the statement about base strength, okay, these species are not bases. If we look at the alkane to act as a base, what do we need? Well, number one, definition of a base. Proton acceptor. To accept protons, what must it have? Electrons. Where are there electrons in the alkane? They're not. So it does not act as a base. When you're referencing your base strength, what are you referencing? The conjugate base. So when you see a weak acid, yes, you can make reference to the strength of the base character, but it's the conjugate base of that acid that is the stronger base. Okay, you have to realize that conjugate is a really important term in that separation. This is where the definitions come in handy, because if I drew that and say, deprotonate that, you should have a mild kind of panic attack. I can't deprotonate that, okay, because that generates an incredibly strong base. The more reactive the base, the less the reaction wants to make it, because we're moving towards a higher energy state. Okay? Questions about those? Okay. Some last kind of big topics that come out of this chapter that, again, don't play as large of a role this semester. There's something known as the leveling effect. It becomes really, really, really important in second semester OChem, and also relevant for biochem. We can't have a stronger acid than our solvent can withstand. Okay, meaning if we take sulfuric acid and we add it to water, Okay. What's the active acid? Okay. Well, I gotta clean some of this space up here. So really what we're saying is we're taking H2SO4, I put it in water. First off, what happens? What do we get? H3O plus, and depending on the level we'll stick with HSO4 minus. Okay, HSO4 minus is actually still a pretty strong acid, and it would probably deprotonate a second time. Let's not stress there. Okay. If I now add a base that I want to react, okay, so we're now saying I add base. What does that base react with? It is going to react mechanistically with hydronium. It will not react with sulfuric acid. Which seems really weird, but we're taking sulfuric acid, and we mix it with a base, and yet the sulfuric acid isn't reacting. The sulfuric acid reacts with our solvent first, because that is our primary reagent, which then turns it to H3O+. H3O+ is now the strongest acid that can exist within water. H3O+ reacts with the base, not sulfuric acid. This is what's known as the leveling effect. Your solvent will dictate the strength of the acid or base that's present. Okay. Relatively minor role as far as getting through organic chemistry. Your textbook references it. I just want you to be aware of what's going on within it. Okay. Kind of makes sense. And it's not that big of a deal, so I'm not all that panicked if it doesn't make sense.
Why do they call it a leveling?
What happens to the strength of the acid? Sulfuric acid is stupidly strong at a pKa of somewhere in the like -7 range. Okay. If I react that with a base, that's going to be a really strong acid-base reaction. Okay. As soon as I throw in water, what happens? I'm now no longer looking at a pKa of -7. I'm looking at a pKa of -1.7. Significantly less acidic. So the acid strength has leveled out, if you will, okay, by minimizing it somewhat. Okay. So that's the intent behind it on where it's coming from. Okay. You get the same thing happening with bases. Again, relatively minor issue. Second semester red flag. If you see amines, we've already kind of tagged this. If you see amines in second semester, you will learn to hate them because they do everything under the sun. Okay? They'll do acid-base reactions, they'll do nucleophile reactions, they just become a mess. Okay? Particularly if you have to deal with an online homework system. Okay? So just watch out for those. Thermodynamics, everybody's favorite topic. Okay? We get Gibbs free energy. Okay? Gibbs free energy, we can look at the products minus our reactants. We get the delta G for the reaction. We can tie that back to our equilibrium constant. Our equilibrium constant is calculated by doing products over reactants. Okay? So we already kind of looked at this by looking at our pKa and predicting where our reaction would go. Okay? Every reaction we're going to want to do this semester, what would we expect for our K? Big or small? Why do we want it to be big? We're trying to make something. If our K is very, very small, what does that mean? The reactant concentration is largest. That's a pretty crappy reaction to run. We're trying to make something, and what we do is we mix all our stuff together and it does nothing. Okay? Generally bad idea. Okay? We want it to react and do something. We want to see large Ks, which means what do we expect for our Gs? We actually want exceptionally small G's. We want very negative delta G's. How could you figure that out? A couple ways. If you take a large K and plug that in, the ln of a large K gets you an even bigger value. Negative of that gets you negative delta G. Okay, so you can solve for it from the equation. How else could you do it? You could remember back to 152. When did you have a spontaneous reaction? Negative delta G's. Okay? So negative delta G, we can use, that's saying our product's more stable than our reactants. Positive delta G's, products are less stable than our reactants. Positive delta G's generally not favored, and sort of we'll never see. And we'll talk about that sort of we'll never see when it pops up. The next fun thing you can address, you can solve for delta G by also looking at delta H, known as the enthalpy, minus T delta S, where delta S is the entropy. Delta H, our enthalpy, is a representative of what? Yeah, it's heat stashed within. So disorder is our standard reference, but not for enthalpy. Disorder is entropy. What is our delta H typically referring to? Our heat found where? Stored where? In our bond energy. So when we change our bonds, as they change, that's our delta H. We could go back again to our second semester Gen Chem and predict something about what we would want for each of those reactions, be it positive or negative. If your enthalpy is greater than 0, then it's an endothermic reaction. It requires energy to get the reaction to go. That is also a non-spontaneous type of situation because we're going up in energy. Okay? Enthalpy being less than 0, okay, is our favored spontaneous situation, exothermic. So we can hear exo and endothermic references. Entropy, I hate the term disorder because it's too nebulous. I refer to motion instead. It does the exact same thing. Okay, if we say disorder increases, what does that mean? Okay. If this room became more disordered, what happens? Less organization. Okay, so we've defined disorder by using less, there's dis, and organization. Okay, well, what did that mean? We still don't have anything physically observable for us to nail down. If we become less ordered, there's going to be a lot more motion. So motion is a much easier way to reference and visually see entropy. Okay? With all that information, yes, we can drop in numbers, we can quantify and all that fun stuff, but instead what I would like to do is look at an energy diagram. Okay? You will continue to see this slide pop up both this semester and next semester if you take it with me. And theoretically, you should have seen something like this in 152, because all 152 is study this diagram. Everything you do in 152 is this diagram. Okay? So we've got reactants shown as R, products, P. We move from reactants to products, what's happening? Okay, we're doing a reaction. So typically on the x-axis we show RXN chord saying we're doing a reaction, that's it. Okay. As we move from reactants to products, we notice that the energy goes up. Okay. And then it goes back down. So in this case, we are looking at a delta G that happens to be negative, less than 0, which would suggest that this reaction is spontaneous. Okay. One of my pseudo pet peeves, because I had to teach 152 long enough and figured everybody's got to deal with that suffering. You will see reference to delta G suddenly become, instead of delta G, delta H. Okay, why do we end up referring to it as delta H instead of delta G? Because it is delta G all the way through.
What's the main form of energy that's coming?
It's our largest contributor to delta G. The change in entropy is usually so insignificant that it doesn't contribute to our overall understanding. So we can end up referring to that distance or that difference between our reactants and our products as delta H, which then allows us to draw some other conclusions, like this reaction being exothermic. I don't know why I erased that. It is still less than 0. Okay. Still spontaneous and all that fun stuff. Okay. Delta G, delta S, all of that are terms that apply solely to thermodynamics. So when we're looking at the distance between our reactant and product energies, all we're concerned about is thermodynamics. Is that reaction something that is likely to occur? Okay. For instance, combustion of wood. When I put fire, oxygen, and wood near each other, what happens? A reaction occurs. It burns. Okay? That is a spontaneous reaction. Okay? And yet, if we take another piece of organic matter, like humans, we don't see it spontaneously combusting. Why not? The thermodynamics, it is exothermic actually, has nothing to do with how fast the reaction occurs. To figure out the speed of the reaction, I need to look at the activation energy, which is then tied to kinetics. Okay? So kinetics and thermodynamics are opposite sides of the same coin. We can use both of those pieces of information to predict something about the speed of our reaction and something about the likelihood of whether or not it will occur. When we look at our acid-base reactions, the only thing we've addressed so far is if it'll occur, which means our thermodynamics. We've not addressed anything to do with kinetics. Okay? There is a delicate balance between kinetics and thermodynamics. In this semester, we primarily deal with thermodynamics. We're assuming that our reactions happen fast enough, we don't worry about it. Okay? Second semester, kinetics becomes much more important. Okay? So, relative strengths of charged and uncharged species. If we go back to our acid-base reactions, we could go through and now apply this into an energy diagram. Okay? So if I take water and have it react with another water molecule in an acid-base reaction, I can form H3O plus and OH minus. Okay. Based on that, what information might we draw or potentially conclude about... Okay, I lost connection. I don't want to ask the question quite yet because I need to make some stuff disappear. What could we possibly conclude about the likelihood of this reaction occurring on its own? Shouldn't happen. Why not?
The pKa is the same, right?
So we could look at pKa's. The pKa's being relatively the same. There's no driving force for the reaction. What else could we look at? Charges. We're going to a charged product. Okay, so we had two answers. We could quantify it. That means we had to know the pKa. Water, fine, we got that. We could also look at the charges. We increase charges. Increasing charge a good thing? No. Okay? So we might predict that that would not be a very good reaction. So to prove that, what could we look at? We could look at the delta G for the reaction. The delta G for that reaction happens to be positive 80 kilojoules. It is not a favorable reaction. Okay? That's why we have that positive value. If we try to draw an energy diagram, there's our energy, there's our reaction coordinate. Since I don't necessarily know where anything is yet, I'm just going to draw my reactant somewhere floating in the middle. Okay. If I have a positive delta G, where should my product energy be? It needs to be higher than it. Okay. I know I have an activation barrier. That activation barrier will happen to be closer in energy to which? The transition state will be closest in energy to the products. Why? The products are higher in energy than the reactants. By necessity, thank you, our transition state is going to be closer in energy to the products. It can't be closer in energy to the reactants because the products are higher in energy than the reactants. Okay? And we now have an energy diagram. Ta-da, that's it. Okay? Could we use this to predict something about reactivity or acid-base reactions? Yeah, we can. So let's take a swing at these two potential acids and put them into an energy diagram. So we're taking CH4 and NH3, and I'm going to react them with water, and I want those species to act as, let me make sure I'm doing this right. Yeah. Yes. I want these species to act like acids. Okay. So first step would be to do what? What's that? Deprotonate the carbon, which means I should end up with what? CH3 minus. I got rid of a positively charged hydrogen. And what else? H3O plus. Number one, should I expect this reaction to go? Why not? I've built charge. So that inherently makes me go, that's a bad idea. Okay. How about the other one? And? Okay. Reactant energy. Okay, would I expect the starting energy for the CH4 or the NH3 to be much different? Not really. They're both neutral. We could try and do some predictions of that, but for the most part, they're going to be pretty close in energy. So let's start with just the CH3 first, and we'll do our reactant energy. What would we expect to happen for our product? Should it go higher in energy? So let's draw it up here. Should it go really high in energy or just kind of low at the bottom? Okay, kind of high. Why? CH4 is neutral. CH3 minus is charged. Okay, so it should be higher in energy. Well, but maybe carbon can hold a negative charge. If it can hold a negative charge, then fine. It should drop its energy a little bit because it's allowed to. Can carbon hold a negative charge? No. Why not? Small. Very good first reason to start with. Next reason. Not very electronegative. Next reason. No resonance. I'm very happy right now. Thank you. Last reason. No inductive effect. Okay? We're using those same rules that we've been using to apply our acid strengths. Everything says that should be significantly higher in energy. So I'm going to draw my product energy really high up there. I'm going to do CH3 minus. Okay. Flesh this out. There's my big curve. There we go. CH3 minus. Any questions about that? So now the challenge. NH3. Okay. Its reactant energy, saying is starting roughly at the same position. Might actually be a little bit higher. Okay. But for the most part, starting at roughly the same position. Where's the product energy going to be? Why should it be lower? Okay, so it's lower in energy. Okay. Frame of reference, good call. Yeah, maybe I wasn't listening carefully enough. Okay. Your product energy should still be higher in energy than the reactant because it's charged. Okay. Should it be higher in energy than the CH3 minus, than the other one? No. Why not? Why can nitrogen hold a charge better than carbon? It's more electronegative, which means when I draw my NH3, it needs to be lower in energy than the CH3. No. Can't do resonance on itself. We can finish out our curve. Okay. Which of these reactions would we expect to happen faster? The NH2 minus. Why? Why would the activation energy start to drop? What determines the height of the activation energy? Either the reactant or product that it is closest in energy to. What is it closer in energy to? The product. The product is lower in energy than our other CH3, which should suggest what of the activation energy for our should also drop a little bit lower. So we end up seeing two things potentially contribute to NH3 acting as an acid before CH4. Number one it generates a more stable product. Number two, should react a little bit faster because the activation barrier drops. The exact values by how much these things change, you'd have to go through and quantify. Right? And this is another fun thing that we can bring up. You can absolutely quantify everything in organic chemistry. It's known as physical organic chemistry, and there's some really cool things that come out of it. Okay? To quantify all of those values might take the rest of the day as far as explaining calculations and running experiments. By just looking at it, we've come up with an approximation that gets us within 90% of being 100% correct. Which makes more sense to work with? The 90%. So yes, we are a little bit wrong, but it's close enough. That is the beauty in organic chemistry, and that ultimately is the beauty in all science. Okay? I asked you a test question in lab. How do you separate salt from sand? Okay? And it's a question that most people tend to panic with, because when we think about science, we think about, oh crap, it's got to be complex, I got to do something crazy with it. Salt dissolves in water. Sand does not. Add water, filter, done. Don't make it more complicated than you have to. Okay? If we have the ability to go simple, do it. If you want to quantify later, you can talk to me forever outside of class. Okay? I might get sick of it, but we could potentially go through all of that. There was a question back there.
Yeah, so what I was thinking, so if you had a reaction around negative delta G, the product was below the reactants, the activation energy would be less than all of the other two as well?
So if we switch this reaction around to it now being endothermic, what ends up happening? What happens to the activation energy? It might drop a little bit for the purple one because the product energy is lower. But if our reactant energies start at the same level, what happens? The transition state. Roughly the same, because the transition is closer in energy to the reactant. If there's no change of energy at the reactant, what happens to the transition state? Virtually no change in the energy there. Okay? We do see some slight changes, and those changes can be significant enough, but under most circumstances, that ends up not changing the speed of our reaction. And we end up finding some other reason to go through and explain what's happening there. Okay. So here's what your textbooks put together. Prettier slide than what I drew up. We've got all the reactions drawn on there, all the exact same pieces doing the exact same ideas. What if we draw on HCl? Where would we expect HCl? Okay. Even lower in energy. It happens to transition so low in energy that it's an exothermic reaction, probably because HCl is a strong acid. Does HCl go counter to our argument here? What happens when I add HCl to water? Would I expect this reaction to occur? We heard some no's. Why? There's more charge. Okay. Does our charge analysis always work? No. Is there something else competing here? Yeah. It's going to be the stability of that chloride ion. Okay. Why does this reaction relatively exothermic? Chloride could stabilize that negative charge really well, even though it's charged. Why? Very large and very electronegative. Do they counteract rule number one? Yes. Okay. There will always be exceptions. It's a question of, do we care about that exception? Why is this one that I would almost always try to dodge and say, you shouldn't even be looking at this as an exception? What can you tell me about HCl? It's a strong acid. By definition, what do strong acids do? They completely dissociate into the ions. They dump off the hydrogen. You should be doing that. Okay. Why? The nasty dodge is because it's a strong acid. We defined it. Okay. The other way it goes back to saying, yes, the chloride ion is now low enough in energy it counteracts. Okay. Questions about that? Okay. Ion stability. Okay, so I kind of flipped this one on the head. What makes each of these species unstable? The charges. All of these are unstable because they are all charged. Okay? So that's our number one thing. But now I'm asking you to say, I don't care if they're stable or unstable, rank them. Which one is more stable than all the others? Okay. You might be thinking back to mass spec. And in mass spec, the more substituted, the more stable was our reference. We said, don't worry about it quite yet. It'll come up again. Here's where it's going to come up again when we start to look at reactions. Our reasoning behind it was defining what was reactive. What is reactive here? And I need a little bit more information than the charge. What about the central carbon makes it reactive? Yes, it can accept a proton, but why can it accept a proton? It has an extra pair of electrons. That's why it is negatively charged. Okay, we can imply lone pairs. There is a lone pair implied in every single one of those center carbons. That's what the negative sign is telling us. Okay? So those are reactive because that carbon has an extra lone pair and it wants to share some of those electrons with something else. What would make that carbon less reactive? A bond. We shared those electrons with another atom. Does that help us rank these? No, because we can share those electrons with every single one of these with another atom. That doesn't help. Okay, so we need to look somewhere within those structures to determine something about them. Okay, we want those electrons to be dumped somewhere else. Can I move those electrons to another atom in those structures? As drawn? No. So crap, I cannot look at resonance effects to stabilize these. What do I then need to look for? An inductive effect. Okay. So we need to be looking at the atoms around our center atom and say, what can those atoms do different in each of those cases? So let's pick our extremes, the top versus the bottom. What's our primary difference? Carbon versus hydrogen. What is our difference between carbon and hydrogen? Size, pause. Do we care about the size? No. Size is only relevant when we're looking at the atom that is holding the charge. Neither the hydrogen nor the carbon on the outside are holding the charge. So size is not relevant here. We could look at electronegativity. Also ends up getting dicey. What else is a difference between carbon and hydrogen? What was that? Interesting. There's a differing number of electrons on carbon versus hydrogen. Okay, well, size didn't really matter. Electronegativity is almost the same. A different number of electrons. Would that matter? I don't know. How many electrons does carbon have extra over hydrogen? Okay, 3. I'll accept that as a number. What would make our center carbon more reactive?
More charge?
What charge?
More of a negative charge?
More of a negative charge. So we looked at trying to stabilize it by bringing something else in. Okay? We could look at something to stabilize it by looking on the outside. That would be a resonance effect. We couldn't find that. So now what we've got to do is look at those atoms and see what difference they contribute. The carbons bring in what? Electrons. What did we do to the effective negative charge? We've put more electrons around something that already had a ton of electrons. The result is more negative. Is that more or less stable? That is less stable. What happens in the other case? We have less electrons around it, which should suggest less negative, which then means more stable. What happens as we move from the top to the bottom as far as the amount of electrons? Slowly increases until we get to a maximum in the bottom, which makes us the least stable. Okay? You might think, well, wasn't that opposite of what we had talked about before? No. No, it actually wasn't. Okay? Feel free to go back and check your notes. It's not. Okay? Why is this? Why are you now thinking that it is opposite? What did we look at before?
It's not heated combustion. That was the more obvious.
We looked at positive charge. What are we looking at now? Negative charge. Has our definition changed? What we are applying our rules to has changed. When we go through and look at acid strength versus base strength, we use the same set of rules, but what changed? The definition, our starting point. Same thing is happening here. This is true. These zero area or methyl anion is the most stable out of this set. But what would happen if, say, I switched it to a carbocation? What makes the carbocation reactive? Positive charge. How can I make the positive charge more stable? Give it more electrons. And now what happens? The more stable becomes the bottom one versus the top. Okay? You have to be careful in what you are referencing when you're looking at these. It's not just saying, oh, tertiary is always more stable. No. What is it that is making it unstable? What is it that is making it more reactive? Once you've identified that piece, now you can start to answer your question. The rote memorization of tertiary is better than secondary, better than primary, will get you through maybe 50%. 50% on an exam is not something I want to see. Okay? You need to apply your definitions, identify the reactive thing, and start moving slowly outward from there. You did have a question, Tyler?
Yes, just when I saw the negative charge species, so the electrons on the carbons and outside on the tertiary portion are like kind of just holding that negative charge closer to the carbon.
You can look at it that way, because I do make that argument, if you want to keep going.
Making it like less space, less size for those electrons to cover, and just like pushing them in the center.
If we can, no, I'm not sure actually I like that.
I could be wrong.
Because if those electrons need to come out, they'd have to get by these electrons. So by that logic, to me, that would be saying this is the most stable because those electrons can't react.
No, because how we talked about how like size, how electrons can move if they're spread out across a larger surface area. With that, you're making the surface area a bit smaller. Maybe just minutely.
It's a thin argument. It's not one I want to reiterate for the recording. As long as you get it right, I'll accept that.
Okay.
Does that make sense?
If for the center row, would it follow the same trend as the negative?
If we look at that center row, what's happening in there? Probably my least favorite sequence of reactions. Those are all known as radicals. Radical reactions pretty much do whatever the hell they feel like. It's a little bit less nasty than that, but it's pretty close. You'll probably learn to hate them if you have me as a teacher. If you move on to somebody else, maybe you'll learn to love them. What makes radicals reactive? It's not even just an unbonded electron, because the anion has an unbonded electron too. But the anion can make a bond. Can the radical make a bond? No, why not? It's missing an electron. So what's the issue of radicals? They're reactive because they are missing an electron. Which best matches missing an electron? Cations or anions? Cations. Your radicals act mostly like cations, much less like anions. Okay? And it's that missing electron feature. Questions? Okay. This kind of gets back to our acid-base deals on what's going on within those. Anybody recognize structure up there? What's that? There is a carboxylic acid. I'll accept that. What's that one? An amine. So I have an amine and an acid. I have an amino acid. It's our basic building block for proteins. Amino acids. Okay. The amine end tends to act as a base. The acid end tends to act as an acid. Depending on the pH, what happens? If we are incredibly acidic, we keep the hydrogen attached to both functional groups. As we increase the pH, we become more basic, and we start to lose hydrogens. What does that do to the molecule? As a sort of hint. Versus. We don't even need to evaluate stability here. First structure is +1. Next structure is 0. Next structure is -1. Do we get different interactions between these molecules in their environments? Yeah. Pretty hugely different interactions. These contribute to actual actually they don't contribute to protein fold. Contribute to reactivity of the amino acids and potentially isolating and determining the sequence of your amino acids within a protein. Okay? So we can change and fluctuate pH to isolate different amino groups. Okay? So if we have a species with more than one acid or base functional group, we have to be very careful when we're monitoring pH, particularly if we're dealing in a water environment, which we would be in biochem. To deal with that, we'd be going all the way back to everybody's favorite, the Henderson-Hasselbalch equation. How many people have not heard of Henderson-Hasselbalch? Really? Okay. I met one Gen Chem instructor that refused to use it because everybody screwed it up. Okay, so he just made everybody do it longhand. It was fine. Okay, so Henderson-Hasselbalch, you remember that? Go back and solve all that fun stuff. Super exciting deal. What we end up learning out of it, let's see, did I put it up here? Whoop, nope, I didn't. That was nice. We can use that information to our advantage in a water environment, and we can compare the pH that we're at to the pKa of each functional group. What was the pKa for the amine? It was 35 and 9. Remember, we have to be careful with that. It was the 9 we needed to worry about. Sorry. Not that I'm color coding too much here. Our amine pKa was a 9. The acid pKa was, we said, roughly 4. It turns out when we move to the carboxylic acid, what would happen to the pKa? Or sorry, the amino acid. What do you think would happen to the pKa? We have the acid functional group. Compare along, what is nitrogen? Yes, nitrogen is a base, but more in general. An electronegative element, which then means we have an inductive effect. The acidity of your carboxylic acid actually drops. The pKa for most amino acids is in the 2 range. It's like 2.2, I think, and 9.1, something like that. Okay. So how could we use this? Well, what happens if we're at a pH of 1? Okay, well, this gets a bit weird, but our pKa is greater than our pH at 1. So what does that mean? We are in a more acidic environment than our functional group. For a more acidic environment, what should happen to the protonation state? It should be protonated. So at a pH of 1, what do we have? Hydrogens attached. What happens if we look at the amino group? The pH is 1. It is still more acidic than the pKa of our functional group, which means I need to be in the protonated state. That first structure is at a pH less than 2, so pH of 1 works. pH for the middle structure. Any ideas for a pH? Between 2 and 9. Greater than 2, less than 9. Last one. It's a pH greater than 9. Okay? That can allow us to then determine what charge state we've got by doing a quick comparison. For those of you that don't believe me, have fun with the Henderson-Hasselbalch equation. Okay? You're more than welcome to do that. Okay? But that's what we can end up pulling out of that, is we can look at the relationship between the pKa and the pH. Okay? Questions on that? Okay. Chapter 7, very little I'm going to talk about within Chapter 7. This happens to be one of them. They make reference to electron-rich and electron-poor. Okay, these are all coming down to electronegativity differences. For those of you that printed this out, you probably know there's a big bunch of black boxes at the bottom of the page. I drew all those figures. I inserted them into my PowerPoint slide, and for some reason, PowerPoint has decided that I'm not allowed to show them, and so has turned them into black boxes. I have no idea what structures I drew down there, so I couldn't even go back to add those figures in. But I did at least delete them from this, and we can look at some examples as potential guesses. Electron-rich. If you have an electron-rich atom, that can also be referred to as an electron donor. Okay? Electron donors tend to be negatively charged because electrons are negatively charged. If we have more electrons, it should become negatively charged. Okay? This would then correlate or match to LB. BB and N. LB. LeBlanc, nice. No. In fact, the LE off of LeBlanc wasn't too bad. Lewis. It's a Lewis base, a Bronsted base, or a nucleophile. Okay. These typically have high electronegativities. So atoms that are generating Lewis bases or nucleophiles tend to be more electronegative than other atoms. Why? What happens if you're an electronegative element? You attract electrons to you, which then means you become negatively charged and you fit the definition of electron-rich. Okay? You'll typically also see nonmetals to metals as a big signifier there. So if you bond a nonmetal to a metal, why would you end up seeing that as an electron-rich atom? Well, what's the difference between nonmetals and metals when it comes to electronegativity? Say that again? You got the right idea, you're probably just saying it wrong. Metals are not electronegative, not more, but less electronegative. Okay, within our periodic table. So if we took a look at some classic examples here, let's say, actually let's just do this one. Why would we expect that one to be electron, or would we expect it to be electron rich or electron poor? We didn't even define electron poor, so you should already guess. It's electron rich. Why is that compound electron rich? Oxygen, high electronegativity. It's bonded to a metal, so we could split that, and the oxygen would carry a negative charge, which then means still electron rich, and it could act as an electron donor. If we reacted hydroxide, say, with an acid, what does it do? Donates its electrons to a hydrogen. It was an electron donor, which then makes it a Lewis base. To make it a Bronsted base, how would we change that statement? It's a proton acceptor. Okay. What if we wrote out this instead? Actually, let's just stick with that one. What do you think? That's harder. Any guesses? Worst case, you're wrong. Electron rich. Good, you weren't wrong. Okay. It is electron rich. Right? Not very obviously. Why might it be electron rich? You have those double bonds. Those double bonds are going to make it electron rich. Why are those double bonds particularly reactive? Higher in energy because pi bonds made with p orbitals, which are higher in energy. More or less electron rich? Why more? Yep. We've got the metal there, which means the electrons in that bond spend most of their time on the carbon, making the carbon negative. There's our electron-rich source. How many of you are going, why did you put a negative charge on carbon? Carbon can't hold a negative charge. Anybody? Anybody? The metal drops off. Okay? That carbon is exceptionally reactive. Okay? We'll learn about it in second semester. Okay? It is a carbon that can act as a Bronsted base or a nucleophile. Super, super rare to get carbon to do that. What if we switched over to the electron poor? Our electron poor atoms will end up being electron acceptors. They are typically positively charged because they're missing electrons. These will be our Lewis acids, Bronsted acids, and electrophiles. These are typically atoms that have very low electronegativities, okay? Because something else needs to steal electrons from them to make them positive. Okay? These become much trickier to deal with. You're typically looking at your nonmetals being attached to a more electronegative nonmetal. Okay? So some interesting examples. Where's our electron poor atom? Sorry, I think blue is a problem for the back. Chlorine actually won't be electron poor. The chlorine has its full octet, but so does every atom. Chlorine is also not positively charged. Typically low electronegativity. Chlorine's one of the higher ones. It pulls it from the carbon, making the carbon positive. There's our electron poor atom. It's actually the carbon. Why did the chlorine not act as an electron-rich atom? It's high electronegativity. It has electrons. It isn't, well, it's not a nonmetal to a metal, but it is a nonmetal to a less electronegative metal.
Is it because it's not negatively charged?
Kind of, sort of, indirectly. How many bonds can your halogens have? One. How many bonds does chlorine already have? Can it share more electrons? No, because then it becomes positively charged. So the chlorine ends up not acting as an electron-rich atom in this case because it can't share any more electrons. Okay? So sometimes you can be like, oh yeah, I get it. Electron-rich tend to be pretty easy. Electron-poor can be very confusing to deal with. Do the best that you can within those. One more quick example on those. Electron rich or electron poor? Oh, good answer, and I color coded the other direction. So yes, electron poor. Which atom is the electron poor atom? For those of you saying the oxygen, unfortunately you are wrong. It's the hydrogen. Why is it the hydrogen? The oxygen is greedy. The positive charge helps us look for, at least where the reactivity is, it does not necessarily signify it. That oxygen being positively charged, okay, kind of fits in that electron poor category, but that means it would need to be able to accept more electrons. How many electrons are currently around the oxygen? None. Or sorry, 8. There are 8 electrons. It can't accept more electrons. Okay, so it can't possibly go higher. Okay. What about the hydrogen? It's low electronegativity being bound to a high electronegativity atom which means the electrons in that bond spend most of their time where? On the oxygen, which then does what to the positive charge on the oxygen? Neutralizes the charge on the oxygen. The hydrogen ends up being the electron deficient one. This is where another atom can come and share electrons with that hydrogen. Yes, we see bonds breaking and making in both cases. Right? So your electron poor can be difficult. It takes a little bit of practice getting used to those, seeing how electrons can shift around. Okay? So, with that, fun quiz. There is kind of a hand-wavy argument behind that, which is down here at the bottom, like my little hand-wavy. What is the hybridization of the oxygen and carbon in each of these two final answers? So our target oxygen versus our target carbon. What is the hybridization? sp2. Which hybridization state would be preferred? Well, which element is more electronegative? Oxygen. So if oxygen is more electronegative, it would likely want to be in the most electronegative hybridization state, which would be sp2. Okay, or sp, but we can't get to sp. So we'd be at sp2. That can kind of explain that. Okay. This relationship is an important relationship. It explains a lot of chemistry in biochem and explains a lot of chemistry you'll see in second semester. We will see this particular relationship show up at the end of this semester when we talk about addition reactions. Okay? So we'll come back to it and talk about it in a lot more detail then. For this moment, just kind of be aware of what's going on within it. The last things I want to address are these initial quick sides. We've got 5 reaction types that you will need to learn and understand by the end of the semester. We've talked about acid-base. We'll be looking at substitution and elimination in this next unit, or the unit we're currently in. And then after exam 3, we'll be looking at addition and radical reactions. Okay? Look and study those general forms. Those will help you recognize what type of reaction is occurring. Once you know the type of reaction, you can then start to draw predictive abilities out of it. Those predictive abilities, this may look like a foreign language up here right now. What we've got summarized up here are your substitution reactions and your eliminations. And it turns out when we look at each of those 2 reactions, there are 2 primary mechanisms for each. We name those SN1, SN2, E1, E2, really creative. The first type of mechanism, the second type of mechanism. Right? There is a little bit more meaning behind that. Within each of these, you are looking at a rate. Thank you, kinetics, substrate, nucleophile, and solvent. What we've got in here are some preferences. So if you look at a reaction, you're going to want to predict which mechanism do you get, SN1 or SN2. Well, if you have a primary substrate, which mechanism would you expect? SN2, because it follows under that column. There are lots of these kind of summary slides scattered kind of around. Okay. Once you've established the mechanism, you then have to worry about complications of each of those mechanisms. Each of those details we'll be talking about this week and next week, and then one more day, and then you get your exam, I think. So we get 4 lectures left to go through all of these. These are your big summary slides that cover all of the bases. We'll look at the details of each of those in the coming lectures.